All right, so in that case, let us start today's topic. So we are moving towards a more formal exploration of Lie groups and Lie algebras. So today, we are going to do some warm-ups. So our topic today is going to be Lie groups and Lie algebras of matrix groups. Okay, so what are matrix groups? Matrix groups are groups which are defined by matrices. Okay, so now so far, we have seen some continuous groups. So continuous groups are also known as Lie groups. That are defined in terms of matrices. So the groups like GL and R and GL and C, these are kind of the master matrix groups. A lot of the matrix groups we're interested in are going to be subgroups of these groups. Okay, so we have met those, right? But we have met other Lie groups. So for example, U1, SO2, and we found that these are actually isomorphic. And then we got O2, which is SO2 is a subgroup of O2. O2 has a disconnected component. And then we have also had the rotation group SO3, and of course it sits inside O3. And then we had SU2. So these are all examples of groups which are compact Lie groups. So what do I mean by compact? By compact, I mean that the parameter space, so by compact, we mean that the parameter space or the group manifold is a compact manifold. That is, it has finite volume. Okay, so for example, U1 is SO2 and it's a circle. It's a circle. Okay. And we also saw that SO3 is isomorphic to SU2 over Z2, where SU2 is a three-dimensional sphere. So SO3 is a group which is not connected. It's not simply connected, sorry. Now you might say, what about O3 or O2? Now O3 and O2 can be thought of as having, an island which is connected to the identity, which is SO3, and another island, it's a disconnected component. So where you can go from SO3 by applying say the parity operator. Okay, so these are disconnected groups. Okay, so those are disconnected manifolds. Can someone give me an example of a very simple manifold which is disconnected?
The zero sphere, I think, was disconnected.
That's very nice. Thank you. That's exactly the answer I was looking for. But of course, you can say R cross R is a disconnected manifold, right? So, but this is a more interesting example, so to speak. And this is O3 is even more interesting example. Okay, so I hope you understand what a compact manifold is. So we also saw examples of non-compact groups. So R1, SO1, 1, these are non-compact groups. And another group we did not introduce in the lectures, but in the tutorial yesterday was SO1, 3. So this is the Lorentz group in 3 + 1 dimensions, right? 3 spatial dimension and 1 time dimensions, right? And the 3 + 1 dimension. So this is the group which defines the Minkowski space. So a Minkowski space is a space where intervals between 2 points are given by, if delta x mu is an interval between 0.1 and it's a vector, it's a difference between the position vector, then eta mu nu is a rank 2 symmetric tensor, which is of this form, and the transformations of x's, so under some lambda mu nu, delta x nu, 1, 2 here, these guys which leave the interval invariant form a group called O1, 3, and the connected component of that is SO1, 3. Okay, this is mathematically what we know as the Lorentz transformation. So the Lorentz transformation matrix, if you take 1 here, and you look at the 3 by 3 matrix here, then these matrices form the group O3. Okay. These are, in the SO3 part of it are the rotations. Okay.
Sir, in the SO3 thing, there is only one number in the bracket 3, but here 1, 3. So is the 1 different from the 3? Like 1, 3 could be written as 4, right?
Yeah. So SO4, you're saying what is the difference between SO4 and SO1, 3, right?
Yes, sir. How the number is different.
Yeah. So SO4 are 4 by 4 matrices. Say let's call them lambda, which satisfy this equation. Okay. So this is the identity matrix. SO1, 3 are the 4 by 4 matrices lambda, which satisfy, so there's a transpose here, sir, which satisfy this transpose eta, lambda eta, where eta is given by this matrix. Okay, so that's the difference between SO4 and SO1, 3. Okay, I should really be more technically correct and call them O4 and O1, 3. Okay, Farhan, is that correct?
Are these numbers like name conventions, or they could be anything like O5,7 or something like that?
Yeah, I mean, mathematically, there's nothing stopping you from defining O5,7. O5,7 would be 12 by 12 matrices, lambda, such that lambda transpose eta, lambda is, so eta, where eta is going to have 5 time-like
5
and 7 space-like directions. I mean, it's not going to be something physically relevant for us, but mathematically, there is no problem defining such a space.
Yes, sir, understood.
Okay, good questions. Any other questions? Okay, so we shall see that at some point, SO1, 3 is a non-compact group. And you can see that already, because you know that SO1, 1 can be embedded in SO1, 3, right? SO1, 1 is a subgroup of SO1, 3, right? Because if I take an element lambda of SO1, 3 and another element small lambda of SO1, 1, then I can write, for example, there could be small lambda here. That is just, one of the embeddings.